Good morning, everyone. Welcome to the another lecture of Haloalkanes and Haloarenes. So, myself, Suman Singh. So, in the last lecture which I have uploaded, that lecture has got some technical fault. I hope if you have seen that lecture, the sound was not there, right? So, since in the so I have deleted that lecture and I will continue with the in the with that from the beginning. So in the fourth lecture we have, that was my fifth lecture, right? So in the fourth lecture we have discussed about up to ambient nucleophile. Okay, so now today we will learn about organometallic compounds. Okay, so what is this organometallic compound? So if we will define this organometallic compounds are those compounds in which the carbon has a direct bond with metal. Okay, organometallic compounds are those compounds in which the carbon has a direct bond with metal. Okay, or we can say that the carbon like this CMG, or you can say Cu, okay, or CuLi like this, or Cna. Okay, so these are what? These are the organometallic compound. Organometallic compounds are those compounds in which the carbon has a direct bond with metal. Okay, or some more example, you can take the example of Grignard reagent, which is R MgX. Okay, Grignard reagent, Gleeman reagent, Franklin reagent. These are all what? These are organometallic compounds. And always remember that this organometallic compound is one. Organometallic compounds are very powerful nucleophile. Okay. Now, so this was about organometallic compound. Now, next we will see about uh, amphiphilic compound. Okay, amphiphilic, AMPHIPHILIC. Okay, AMPHI PHILIC. Okay, amphiphilic compound. So when we talk about this amphiphilic compounds are those compounds which behave both as an electrophile as well as nucleophile. Okay, amphiphilic compounds are those compounds which behave both as an electrophile as well as nucleophile. As you can see here in this case, this this one, this compound here, when it is behaving as an nucleophile, and here you can see it is behaving as an electrophile, right? And again you can see this compound here, it will, when we will give here, it will behave as an electrophile. When we will give OH, it will behave as a nucleophile. So amphiphilic compounds are those organic compounds which behave both as an electrophile as well as nucleophile. Now next, type of nucleophile. So when we talk about the type of nucleophiles, it is of three type: strong nucleophile, weak nucleophile, and moderate nucleophile. Okay, moderate nucleophile and weak nucleophile. So this one you have to remember, just by you will get it automatically. You will memorize, you will get memorized with this if you will practice the questions then. So these are the, you write it in your copy, or it is given in the notes also, you can see there. Okay, so these are the three types of nucleophile: strong, moderate, and weak nucleophile. So now next is nucleophilicity. So what is nucleophilicity? In the last class also I have told you about the nucleophilicity. Nucleophilicity is what? It is the tendency, of nucleophile to donate its electron to an electron deficient carbon, right? What I have told you, if it is a base, then it will give its electron to hydrogen, and if it is a nucleophile, then it will give its electron to carbon, right? So you can see here in this case, this nucleophile is giving its electron to carbon, electron deficient carbon, right? Here also it leaving group is going here, and this nucleophile is attacking this carbon which is an electron deficient carbon. So you can see here in both this reaction depict a nucleophile reacting with an electrophilic carbon atom, or we can say that in both the cases you can see that the nucleophile is attacking, or nucleophile is reacting with an electrophilic carbon atom. Okay, or we can say electron deficient carbon. Okay, now in the same case, if you talk about the basicity, you can see here what I have told you. Basicity, if it is a base, it will give its electron to hydrogen. Okay, you can see here, if it is a base, it will give its electron to hydrogen. Okay, so you always remember that base give electron to hydrogen, okay, and if it is a nucleophile, it will give its electron to carbon. Always remember this, okay. So here in this case you can see it is giving its electron to hydrogen, that is why it is what, it is a base, okay. Now next, when we talk about the nucleophile is what, as in the previous class also I have given you some idea about this. Nucleophile is what, these are electron rich species having at least one lone pair of electron. As you can see, the definition, it is an electron rich species having at least one lone pair of electron. It can be neutral or positive, negatively charged, or it will and one more thing, it is always a Lewis base, okay. So in this case you can see this NaOH is giving its electron to what, carbon, this electron deficient carbon, right. So that is why it is nucleophile here, and the tendency means how fast it will give its electron to this electron deficient carbon, that will be its nucleophilicity, okay. Now next is what, basicity. So basicity is what, it is the tendency to donate electron pair to hydrogen H plus ion, okay. Basicity is what, it is the tendency to donate electron pair to H plus ion. So all bases are nucleophile. Always remember that all bases are nucleophile, but all nucleophile are not bases all the time, okay. So here in this case you can see this, since this NaOH is giving its electron to this hydrogen, so in this case this NaOH is behaving as a base. But in this, when we talk about this case, in this case, since he was giving his electron to this carbon, that is why it is a nucleophile. But here, since it is giving its electron to hydrogen, that is why it is a base, right. Now next is nucleophilicity. So what is nucleophilicity? Nucleophilicity, as I have already explained you, it is the tendency of the nucleophile to it is the tendency it is a tendency to give electron pair to an electron deficient carbon is defined as nucleophilicity, okay. So there are some of the criteria for nucleophilicity. So what is the criteria? The first criteria is, if we are increasing the electron density at the donor atom, if we are increasing the electron density at the donor atom, then the nucleophilicity will increase. Suppose the nucleophile which is going to give an electron to an electron deficient carbon, if we are increasing the number of electrons to on that nucleophile, then it will give its electron, or it will react with the electron deficient carbon more quickly or more fast, okay. So that is why what we can say, if we are increasing the electron density at the donor atom, and then the nucleophilicity will increase. Now again, after polarization, polarizability or polarization, I hope you have learned this in class 11 in some basic concept of organic chemistry and chemical bonding. In both the chapters, uh, there was about polarization, so I will not discuss that one. So this polarization is what, more polarizable donor atom is a better nucleophile. Means what, the more polarizable the donor atom will be, better nucleophile, okay. And what we can say, that the large size of donor atom increases nucleophilicity. If the donor atom size of the donor atom is large, then it will also increase the nucleophilicity, okay. So I hope you have understood up to this. Now in the next, what we will see, nucleophilicity in affect the um, periodicity, okay. Okay, before that, okay, okay, after this you have understood, I think. And one more thing, when we talk about this nucleophilicity, um, criteria for nucleophilicity here, so one more thing, you always remember that polar protic solvent, in polar protic solvent, we will discuss what is this polar protic solvent. This polar protic solvent are those solvent in which the hydrogen is removable, okay, or what we can say, hydrogen is connected to FON, okay, fluorine, hydrogen and nitrogen, okay. So uh, sorry, the polar protic solvent are those in which hydrogen is removable, okay. So now we will learn about this, what is polar protic solvent. So in polar protic solvent, PPS, in polar protic solvent, this nucleophilicity will be directly proportional to polarizability, okay. Polarizability. Now again, this polarizability will be directly proportional to size of anion. Okay, so what we can say, like this, that H2Se is a better nucleophile than H2S, okay, than H2O. I hope you are understanding this. As the size of the anion is increasing, nucleophilicity is increasing. After that, what we can say, I negative is a better nucleophile than Br negative, okay, then Cl negative, okay, and then F negative, right, F negative. So as the polarizability increases, nucleophilicity increases, and polarizability is directly proportional to size of anion. So now, periodicity. When we talk about the periodicity, in the same period, or we can say nucleophilicity will increase as the size of the nucleophilicity will increase with the increase in size of the atom. Okay, as you can say, in the same period, nucleophilicity is directly proportional to a size. If the size is increasing, size of the atom is increasing, size of the donor atom is increasing in the same period, then nucleophilicity is increasing. And one more thing, this nucleophilicity decreases from left to right in the period. So what we can conclude, that the CH3 is a better nucleophile than NH2, then OH, then F negative. Okay, so in a group, when we talk about the group, this nucleophilicity will increase from top to bottom due to the increase in the size of the donor atom. Okay, we are talking about this polar protic solvent. Okay, so in the group, nucleophilicity will increase from top to bottom due to the increase in the size of the donor atom, but the basicity decreases from top to bottom. Okay, basicity will increase from top to bottom and nucleophilicity will increase from top to bottom. Why nucleophilicity will increase? Because of the because the size of the donor atom is increasing. Okay, so that is why nucleophilicity will also increase. So what we can say, one more example I will give you. We can say like this, right? NH3, one more thing you can see, NH3, if we are taking NH2 negative, or we are taking NH2 minus, here what we can conclude, in the same atom or element, nucleophilicity is directly proportional to negative charge. Okay, as you can see, as the negative charge is increasing, here negative charge is increasing. As the negative charge is increasing, nucleophilicity will always also increase. So what we can write, nucleophilicity is directly proportional to charge. Okay, charge, with charge, negative charge, as you can see here. Okay, now, so this was about the periodicity. After that, we will learn about the alpha effect. Okay, so what is this alpha effect? So before this, before going to this alpha effect, okay, this alpha effect is what, if there is any donor atom, suppose this is oxygen, is a donor atom, okay, carrying a negative charge here. Suppose if any donor atom is there, and with that donor atom, if any atom is attached, okay, if with this donor atom, we are talking about alpha effect. Okay, alpha effect. Okay, alpha effect. So if any donor atom is there, suppose this is an oxygen, is a donor atom carrying a negative charge, and through this donor atom, if any atom is attached, suppose X is attached here. Okay, and it is carrying a lone pair like this. If any atom is attached, and if that atom is carrying a lone pair, as well as if it doesn't have empty d orbital, if it doesn't have empty d orbital, okay, then it will increase the nucleophilicity. Okay, then it will increase the nucleophilicity, and that effect is what, that effect is called alpha effect. Okay, what we can conclude, alpha effect is what, if any donor atom is there, and with through that donor atom, if any atom is attached which is carrying a lone pair, and if that atom doesn't have a vacant d orbital, then it will increase the nucleophilicity. That effect is called alpha effect. Now steric factor on nucleophilicity. So one always keep in mind that the size increases nucleophilicity. As the size increases, mm, what we can conclude, this nucleophilicity will be affected by the steric factor. Okay, steric effect will affect nucleophilicity, but it will not affect basicity. Okay, so this what we can say, size increases, nucleophilicity decreases. Okay, as you can see, as the size of the nucleophile is increasing, as you can see here, this one and this one, when we compare with this and this one, the size of this one is bigger, right, and this one is smaller, so this will be a better nucleophile than this. So what we can say, this as the size of the nucleophile is increasing, nucleophilicity will decrease. You can say, because why, they as because if you can say, you can take the example like this. If two persons are there, if one is of 100 kg and another one is of 50 kg, then if we are asked to if they are doing a running competition, then who will move fast? Of course 50 kg, right? 100 kg will be, it will be difficult for him to move to run, right? So in the same way, if we are increasing the nucleophilicity, the size of the nucleophile, as the size of the nucleophile is increasing, nucleophilicity is decreasing. Okay, as you can see here. So this was about the steric effect on nucleophilicity. Now again, when we talk about the effect of solvent, so in polar protic solvent, whenever there is a polar protic solvent, large nucleophiles are good, and the halide ions show the following order. Okay, when there is a polar protic solvent, then large nucleophiles are good, and the halide ions show the following order. In polar protic solvent, iodine will be a better nucleophile than Br negative, then Cl negative, then fluorine negative. But in polar aprotic solvent, fluorine will be a better nucleophile than chlorine, then bromine, then iodine. Always remember that in polar protic solvent, iodine, bromine, chlorine, and fluorine, and in polar aprotic solvent, there is fluorine, chlorine, bromine, and iodine. Okay, so in polar protic solvent, iodine will be a better nucleophile, and in polar aprotic solvent, this fluorine will be a better nucleophile. Okay, now when we see the relative nucleophilicity in polar protic solvent, this SH negative will be a better nucleophile than I negative, then OH negative, then NH3, then Br negative, Cl negative, F negative, and H2O. This thing you have to remember. If or one thing you can do, you can make a chart here, and you can place whenever where you are studying, so that you can, every time you if there will be in front of your face, you will get you can do the revision easily, right? So you can make the chart of this. Okay, so this is the relative nucleophilicity in polar protic solvent. So what we can say, in polar protic solvent, large nucleophile are good, and the halide ions are following order. The halide ions follow this order. And in polar aprotic solvent, you can see here, this is the order of nucleophilicity. Okay, so this was about the relative nucleophilicity in polar and polar protic and polar aprotic solvent. Here some of the chart is given from where you can compare. Okay, now leaving group. So what is the leaving group? Leaving group is what we, as we have learned when we will learn the SN1 reaction, at that time what we can say as leaving group is what, the group which move out which move out very easily, or we can say that the one who uh, leave the atom, or leave the atom through which it has been attached. Okay, so leaving group is what, we can say leaving group means the one who leave. So just like this, suppose this is a carbon and here some any group is attached, this is leaving group. So what will happen when any nucleophile will attack, or sometimes automatically what it will do to regain the stability, means if it is like this, suppose if it is making a this is a living group and this is making a bond with this carbon. So but this bond is not so stable. So if this living group has got the chance that it is attaching to this X, suppose, okay. So if we will go and attach to with this X, it will gain more stability. So then what it will do, this living group will just leave that carbon, okay. So this tendency is called leaving tendency, okay. So living group are one who leave the carbon to regain the stability. So when we talk about the order of the living group, this I negative will be a better living group, then Br negative, then Cl negative, then F negative, okay. Some of the other living groups are also given here, you can see it is also given in the notes. So these are some of the living groups, okay. Now one more thing, which strongly basic ions rarely act as a living group, okay. The one which is more basic, then it will rarely act as a living group. As you can see here example, it will not behave as a living group. Here also it will not behave as a living group, okay. More strong basic ions rarely act as a living group. After that you can see here the weaker base are better living group, okay. Strong base, as you can see here, strong base are rarely living group and weaker base are better living group. After that, the living group should have a lower bond energy with carbon. If the carbon and the living group, if the bond energy is very low, then it will easily come out, okay. This living group can easily come out. You can say like this, if the bond is not strong, then we can easily break that bond, right. If suppose if we talk about the friendship and all, if our friendship is not so strong, then we can easily break. So that is why, if the energy, in the same way, if the energy of this bond is low, then it will easily break, okay. Or leaving group will easily go. Now again, negative charge should be more stable either by dispersal or delocalization. Negative charge should be more stable either by dispersal or delocalization, okay. Now next is living group ability. As it is, you can see here, this is a better new living group than this, and after that this. And we can say RCOH is a RCOO negative is a better living group than PHO negative, then OH negative, then RO negative. And after that, SH negative is a better living group than OH negative. And here also you can see, right. Now after that, solvent, I have told you, right, we will learn about this solvent. So solvent, when we talk about the solvent are of two type. One is polar protic solvent and another one is polar aprotic solvent. So which one is called polar protic solvent? In which hydrogen is attached to phone, okay, fluorine, oxygen and nitrogen. In those solvent in which hydrogen is attached to phone is called polar protic solvent. Or we can say that if we are in that solvent, if we are giving nitrogen, then hydrogen, if hydrogen is coming out, then that type of solvent is called polar protic solvent. And the solvent in which, when we are giving sodium here, then hydrogen gas is not coming out, then that type of solvent is called polar aprotic solvent. So here the one charge, I hope you have understood this, right. Polar protic solvent are those in which hydrogen is attached to phone, and if we are giving in this sodium, hydrogen will come out. And polar aprotic solvent are those in which, if we are giving sodium, then hydrogen will not come, okay. So here some of the polar protic and some of the polar aprotic examples are given. You can see here, polar protic solvent are water, formic acid, methanol, ethanol and acetic acid, okay. And polar aprotic solvent are the dimethyl sulfonoxide, NN, dimethyl formaldehyde, DMF, what we say. After that, acetonitrile. After that, hexamethyl phosphorus amide, IMPA, and acetone. So these are what? These are the example of polar protic solvent as well as polar aprotic solvent. Okay. After that, this is some of the question. No need to learn it. Okay, leave after this. I hope you have this class you have understood this. Now in the next class we will discuss about the substitution reaction. That is, in the next class we will learn about SN1 reaction. Okay, so keep up to this till that. Thank you.